Okay, so this is chapter two. This is going to be the slides, our revised slide deck that we're going to be using with three. I think I'm going to be using three of the decks. There's chapter one, which I think we've already covered pretty well. Chapters two and three, we're going to be using the new decks, and I'm going to check on chapter four. So basically, this is going to be the lecture that we also cover in class. All right. So the focus of this particular chapter is on what we're called data modeling, right, which is a fundamental piece of database management, database design. This is going to be one of those fundamental building blocks. All right. So a couple things we're going to talk about. What is a data model, why they're important, some of the building blocks, some of the fundamental pieces that we use around this, and then also some of the stuff around um, not just simply the technical stuff and the structure of the data, but also business rules and kind of where this stuff all kind of fits and comes together. All right. Also, we'll talk about some of the major data models, some alternative data models, and kind of some we'll touch upon, I guess, some of the stuff around the levels of abstraction around this. All right. So to start off with, this idea of data modeling, definitional. It's an iterative and progressive process of creating a data model for a problem domain. So there's a couple words we're looking at here. All right. So I think that the one word we want to focus on is the fact that it's iterative. It's not a one-time thing. You don't do it. You don't get it. You don't get it all in the first cut. Actually, what it'll end up doing is you do multiple takes at it, and each take builds upon the previous one. All right. And then this idea of creating a model for a problem domain. So we do a data model based upon a particular set of circumstances. We take a particular set of circumstances, kind of decompose it, figure out what it is, and then use that as the foundations to build the data model itself. The data models, basically what they are, it's a representation, a picture, of complex real-world data structures. Right, so it gives us the ability to kind of grab, because the idea of data is really kind of abstract, or it's something that's in our heads. So what we want to do is the data model is a way of being able to put a representation so we can talk about it and work with it and, basically be able to do stuff with it. All right. And model, as we say, kind of from the high level, is abstraction of a real world object or event. Not all. We have models of different types. In this case, we're modeling data as opposed to airplanes or submarines or whatever other type of model we come up with. So a couple things about the importance of it. It is a fundamental piece of when we're dealing with databases and data structures. Um, you know, first and foremost, it's a communication tool. It's a way of being able to take something abstract like data and organize it and translate it and communicate it around with other people. All right. It gives an overall view of the database, the big picture. A lot of times, in order to uh, be able to deal with something, you got to be able to, you want to be able to understand both the big picture, all the components, how they align, how they work together, and then specific details as you go, as you kind of drive in, especially for things that are made up of different components. Each component will have its own kind of modeling. But the idea of the data model gives us kind of a big overall view. Um, Organized data for different users. The term we like to use is stakeholders. There's different people who will use things. There's business users who will use the data to make decisions. We've got systems administrators, database administrators, who are going to be responsible for doing design of the structure. You have application developers who are going to be responsible for writing the programs that use this data. All right, so it's really kind of a platform that everybody can can wrap their heads around. And as we say, it's an abstraction of for the creation of a good database. So it is a fundamental, when we talk around this idea of databases, this is blocking and tackling. This is a fundamental, starting point for what we need to do. I mean, we need to do it well in order to be successful downstream. Basic building blocks. One of the things to understand about data modeling is there's a lot of different terminology. There's a lot of words are used. The same things can have multiple terms and they kind of mean the same thing. So it's The backstory of relational databases are that they were derived from relational algebra. All right, so there's a mathematical perspective of this. The relational algebra stuff is still, an inherent part of it, but then there's also the practical stuff. All right, so there's a couple different ways, a couple of different words we'll talk about here, but there's three. There's a couple, the basic pieces we're going to talk about is first thing is something called an entity. All right, it's a unique and distinct object used to collect and store data. This is also known as a table. It's also known as a tuple, but in our case, we're going to say, you know, entity is equal to data, or excuse me, entity is equal to a table. All right. So basically, a table is made up of different fields. All right. The definition, I guess, the mathematical definition of that, it would be an attribute of the entity. All right. So an entity is a table that's made up of different attributes. Each attribute being a different field. All right. And then we have this idea of a relationship. All right. The way relational algebra works is it's really what it is. It's based on set theory. All right. So what will happen is you have multiple sets, and you can say, okay, if I have set A and set B, what is the union of those two sets, which is basically everything that's in those two? Or what is the intersection of those two sets, which is everything that is in that's common between those two sets, or what is unique to each set. So basically, the stuff that's only in one set and not in the other. So there's a bunch of um, different types of relationships we deal with when we're talking about relational stuff. So these are once again, these are kind of the big three, the fundamental three. One is something we call one to many. As we say a one to m here. Uh, Next one is many to many, and the third one is one to one. All right. So basically, what that means is for every entry. So, for example, we'll take an. I always like the example because we can always wrap our heads around this. Is the idea of an order, and you put an order into Amazon and you buy different items. All right. So the order is the one. All right, is the unique item or the unique thing we're creating. All right, and then we can buy as many items, as Amazon has. So you can buy one thing, you can buy 100 things, 1,000 things. All right. So the relationship is for every order there are many items in the order. All right. So that's what we call a one to many relationship. A many to many relationship is that you for each item you can have multiple matches between the two. So you'll see multiple. So you'll end up with multiple. Um, there can be multiple items in one table that will match multiple items in another table. All right. And then the third one is what we call one to one. So one to one relationship, for every entry in one table, there is one and only one entry in the other table. All right. So these are the three, and I think as we go through examples, it'll be a little easier to see. But these are the three. Right? There's not 100. There's only three. Um, and finally, we have also this idea of a constraint. Constraint is a set of rules to ensure data integrity. The idea of a database is database. I always like to use this description is databases are based upon rules. All right. So a fundamental building block of a database is you put a rule for everything. All right. So you have a rule around, basically what a field would look like. Like, is it an alphanumeric field? Is it a numeric field? Is it a date field? All right. You can describe the length of the field. Right? How many characters are in that field? Um, and what the idea is, what you will end up, the idea of doing that, by doing that, you can make sure that your data is has a better chance of being correct. The way I say that, because the idea is just because you set a rule doesn't mean somebody can't break a rule or find some way around it. But the idea is it helps. Key word here, it helps ensure. It doesn't guarantee, but it helps improve the data integrity. Now we talked about, there's a couple different things in this universe. So obviously we've got data, which gets modeled into structures, which can be then processed by computers. But then we also have is what we call business rules, and these are kind of the describe what we do with data, or what are the processes, what are the things we do, what the rules are around things. So you combine, what we will end up doing is we will combine the the data structure with the business rules. All right. So, as we said, from a definitional perspective, business rule, brief, precise, unambiguous description of a policy, procedure, or principle. All right. So basically, this is how we do this. This is what this means. All right. For this particular circumstance, we will do these steps. All right. Um, defining the basic build. Once again, as we talk about this, this is like basic building blocks. All right. And part of this, the relationship between the business rules and the data is basically it describes the main and distinguishing characteristics of the data associated with it. All right. So it's part of the thing we use to define it. And so, this idea of a constraint gives us it gives us a piece of it. Business rules gives us another piece. Sources of business rules, basically, it's how the organization runs. Right? So company managers, the people, the decision makers, policymakers in the organization, department managers, written documentation, basically, one of the challenges in a lot of organizations is trying to get consistency, because you have multiple, you have potentially multiple sources of business rules, and so you can have different interpretations of the same rule. So, it's an ongoing process. It's not, once again, this is not something that gets done once. It's something that happens on an ongoing basis. It's not like you do it and you're done. You start it, it's a process. You get to a certain point, then you keep coming and you keep coming at it and keep coming at it and keep coming at it. All right. And this is, actually a lot of times we'll see with systems, this is where the hard work is trying to define what these rules are, who makes the decisions, who are the decision makers, who establishes the rules, how are these rules enforced. All right. So some of the reasons why we want to do this stuff, really, we want to standardize the view of the data. If you have a particular piece of data, and one side of the organization says it's A, and the other side of the organization says it's B, and another side of the organization says it's C, well, you've got a problem. All right. So really, what you want to do is you use the business rules to help standardize the view of the data. As we say again, once again, communication tool, between users and designers. Communication in business is paramount. A lot of times you'll go into organizations and they say, what's the thing you always have to improve? Oh, we always have to improve communication, because you've got a lot of different people focused in different areas with different perspectives. So this idea of using, the business rules as a communication tool is important, right? And in addition, trying to get the users to talk and use the same terminology and the same concepts and the same perspectives as the people doing the applications and the designers, the database designers, application designers. When this is done well, when this is well established, it really allows a designer to understand, what's going on with the business processes, um, developing what is the proper relationship, and the constraints about different procedures and processes. And third and foremost, you want to have as accurate a data model as possible. The term that gets used is garbage in, garbage out. So if you have bad data, there's nothing a computer can do on its own about bad data. If you have bad data and you run it into a process, you run it into a computer system, and it comes out, it doesn't necessarily make the data any better. Just the fact that you ran it through a computer. You have to. There's work that has to be done to ensure the data, is as accurate as possible. So this translation of business rules and the data model components, this is kind of this is not a straight, not necessarily a straight line, but these are some of the things we do. So you'll see, like, define, translate nouns into entities or tables. All right. Verbs will translate into relationships among the different tables. And then the relationships are bi-directional. All right. So it depends on the perspective of where you are at. If you're table A, all right, so you have a one-to-many relationship. All right. From one table's perspective, it, you understand it as for every entry in the one table, there will be many in the other table. And there's a countervailing of reverse of that, which says, the relationship of a table, where you have many, to the other side is a one. All right. So as we say, some of the things we do, trying to determine what this relationship type is all about. So how many instances of A are related to one instance of excuse me, how many instances of A are related to one instance of B are related to one instance of A, and conversely, how many instances of A are related to one instance of B. Um, Naming conventions. You can call anything you want. You can call a table, an entity, anything you want in a database. You can name all of the attributes, anything you want. All right. Practically speaking, a best practice, the thing you really want to do is you want to use as descriptive of name as possible. If something is an order, if there's a table that contains order information, you want to call that table orders. All right. If it has line items, you want to call the table line items. If it has invoices, you want to call the table invoices. All right. Sometimes people will put like ABC, XYZ. You can put whatever you want as the name, but the more descriptive, the better you are. All right. Because you won't forget, we're trying to model real world things. All right. So you want to use terminology that's familiar to users. Um, Same thing as with attributes. Same thing as the fields. Required to be descriptive of the data represented by that particular attribute or field. And why we do this stuff, facilitates communication and promotes self-documentation. I mean, documentation, you know, what will happen is as we develop applications, it's not once again that's not a one-time thing. You basically will develop say an initial version of a product or a program, and then what will happen is subsequently we'll come back in and make adjustments to it. And sometimes the person who's making the adjustments will not be the person who did the original writing. All right, or it could be somebody, a couple years or a couple iterations down the road. So this idea of trying to describe this stuff in such a fashion so you can you can come back in and maintain it and sustain it is really, is a key part. We talked about different types of databases. All right. So we talked about relational databases. So basically, what we talked about, this relational model based upon relational algebra, is one type. Hierarchical, but there are other database models. All right. So it's not the only one. Relational is not the only one. Hierarchical models were developed in the '60s. Around, actually, it was originally developed by IBM. One of IBM's contributions to the Apollo program was the development of a hierarchical database they called IMS, which was really designed to help them track all of the components in the Saturn V, a couple million components in a Saturn V rocket. And trying to stay on top of that and keep that organized was of paramount importance. All right, network. So basically, what this does from a hierarchical model, if you can imagine, it's a top down with as you go down, it's like a tree. So if you can imagine what we call it, as we say here, it's an upside down tree that basically has a relationship of one to many. All right, so each parent can have many children. All right, so it's a set of one to many relationships from top to bottom. All right, a network model is actually kind of a similar fashion, except it doesn't have the constraint of the one to many. So you can actually have a record. A lower level can have more than one parent. All right. So it was, it did some additional work around, some additional improvements around it. Both of these, there's probably a couple of them still around. Some organizations might still use them, but for the most part, most commercial databases these days, the model we use is the relational model. Yeah. Some terminology, more terminology. Idea of a schema. So a schema, we define that as, it's the organization of the entire database as defined by the database administrator. All right. So basically, it's a picture. Schema is, all the definitions of everything. Remember, databases are based on rules. It's the collection of all the rules and put into a fashion that somebody can work with. Right? And subschema is basically a piece of that. These systems can be, these databases can be very large and very complicated. As I said, For ERP systems, the number of tables that are or entities in that, 100,000. So it's a pretty big, it's a pretty big, complicated piece of technology. So this idea of sub schemas, so you'd have an overall schema with the 100,000, then sub schemas that would represent smaller pieces of it that we kind of combine them all together. There's a concept around in the databases of how we work with the database. All right, so there's two, basically what there is, and we'll be going into this more in depth, but just to kind of introduce the concepts here. There's something we call a data manipulation language. So basically, it's a programming language that lets you talk to the database and lets you do stuff with the database. All right, so the two things we really do with databases. Number one is we manipulate it. So what that means is um, we basically will use it to access data, to be able to change data, to be able to work with the data in the database. All right. Um, and then we have this other type of language called the data definition language, a DDL. Right? DDL is basically lets you define what the structure is, defines the rules. This is what this table looks like. It has 25 fields. The fields are called this. That's actually done in what programming, basically a programming language. Right? And we'll go more into depth. So this is called, just to introduce the concept, this is what we'll be calling SQL, or structured query language, which is once again a fundamental building block of databases. We talking about this, the relational model. So what it was is basically it became really the mainstream. So it started off as 50 years ago. I think in June will be the publishing of a paper by Dr. E.F. Codd, who basically put this whole idea out there, a theoretical model, which all through the 70s was translated into actual programs and software implementations, based on the idea of a relation. All right, so a relation is a matrix composed of intersecting tuple and attribute. So rows and columns. It's another our definition. So a tuple is a row. All right, an attribute is a column. So what it is you think it's a matrix. All right, and what in addition, what it does is it also establishes a set of rules for how you construct this stuff to be able to get the data out. All right, you can't just slap all this stuff together and expect it to work. What will happen is the real um, challenge dealing with this stuff is being able to create something that will allow us to apply these relational principles against the data and be able to get the results, and the results we get are correct. So the idea is that you can always get results out of a database. Challenge is getting correct results out of the database. So in our relational database management system, right, so this is actually the software. All right, so when we talk about with the structure, the tables, the tuples, the rows, the columns, all of those concepts are really talk about the structure, and which is maintained in a file. All right, the DBMS, or you can use different terms, relational database management system or database management system, or DBMS, or DBMS is a program, a very sophisticated program that allows us as people to work with the database. All right, basically provides the fundamental um, capabilities for us as people to be able to create databases, maintain databases, and use databases. What it does is it's a complicated program of itself in and of itself, and what it does is it actually hides the complexities of all of this stuff, of where the data is physically stored and how do we get to it and how do we get after it. So these are pretty you know pretty complicated pieces of software, which are all basically we'll be using MySQL as our example of our DBMS in this course. But remember, so the difference is the database is file structures and files, and kind of the way things are laid out. Our DBMS, database management system, is the software that actually makes the database work. And here's a picture of it. Pictorially, what we have is um, this is a two table database. All right. And actually, this diagram, this relation, this picture right here actually tells us a fair amount. It tells us we've got two tables. It tells us what all the fields are or attributes of that table. It shows with this line here. It tells us what the um, that these two tables are connected, and there's a common field. In this case, it's called agent code. All right. So that there's an agent code in here and an agent code in here, which is the thing that ties them two together. Um, and then you also see these little symbols right here. So on this side we have a 1. On this side we have an infinity sign. It doesn't translate that well, but that is an infinity sign. So the idea is this is a what we would call a one-to-many relationship. For every agent that is out there, so like an insurance company, you have agents that are selling policies. For every agent, they will have multiple customers, one to many. All right. For every customer, they will only have one agent. Right? So if we look at this, this is another example of the one to many. We'll see a lot of examples of the one to many. Right? Once again, that becomes one of those fundamental pieces of databases and relational systems. So an SQL based relational database application. So what this is a piece of software that's designed to work with a relational database and the tables that are contained within. Right? So there's two parts to it. One is the end user. All right. So basically, it's the screen that you and me, as people, will work with. And then there behind the scenes, we have a collection of tables, that are managed by the DBMS that the application will talk to. Right? So as we say here, each table is independent from one another. The rows of different tables are related by common values. All right. And we'll see more and more of this. In order for two tables to talk to each other, you have to have something common. If you don't have anything common, then they cannot be related, not related. So I always like the extreme example of apples to snowplows. So there's nothing between an apple and a snowplow that are necessarily common. So you can't link an apple to a snowplow unless you can come up with some common attribute that ties the two together. Um, the part of the database management system is something called an SQL engine. So what the SQL engine will do, SQL engine will take a request from an end user through this end user interface, translate it into a question or a query, which we would give to the DBMS, which will then look up the data and then return the results when it comes back. All right. So the representation, we talked earlier about modeling. So we talked about an entity relationship model, ERD. What it is, it's in effect, this is right here, what we see right here. This is an example of an ERD, entity relationship models. The idea being each one of these is an entity. Each table translates to an entity. And there's a relationship between them. And so it's the graphic representation of it. Right? It's the entity instance or entity occurrence rows in the relational table. Connectivity is the term to link the two together. So the line we have linked the two together really gives you a pictorial representation of how those two tables are connected to each other. All right. So the idea is you can come in, if you have an ERD for a database, you can get a pretty good sense of how things are structured. And if you do a good job with the naming, it becomes maybe not totally self-documenting, but you can get a pretty good sense of how the stuff is representing, or kind of what the model is, or what the application is it's supporting. There's a couple different ways of doing this. So there's what we call a Chen notation, the crow's foot notation, or a UML class diagram notation. If you look at these three. Basically, what you're seeing here is the same model represented in a different notation. Right? All three mean the exact same thing. All right. So this first one here, a one-to-many relationship. A painter can paint many paintings, and a painting is painted by one painter. All right. So this is you know, this crow's foot is that's the one to many, all right, kind of representation. In UML, it's kind of represented by some numbers here. In this one is your your notation kind of puts a diamond in between with a verb in between to kind of describe the relationship. All right. So a couple different databases. We talked about relational, we talked about hierarchical, we talked about network. A couple other things we've seen: object-oriented databases. You know, it's it was became kind of a thing for a while. I haven't quite seen as much of that recently. It was I won't call it a fad, but it was something that get put into databases. But for the most part, you don't see a lot of, you don't see, I have not seen a lot of large, complicated database applications that are based upon object oriented. But they are out there, and there are some use cases, where it would be an appropriate tool. So basically, what it does is, the idea is an object would contain the data, and all of, it becomes, an object becomes everything you need to know about both the data and all the stuff, all how they're all related, are all contained within an object. All right. Work is tied in well with like programming languages like Java, which were object-oriented languages. So that's kind of where this when as Java really became kind of a mainstream programming language. That's kind of where this idea of object-oriented everything kind of popped up. Object-oriented data model. So a couple terminologies which you'll see in any type of object-oriented anything. Object-oriented programming languages, object-oriented uh, data structures. Concept of a class. So a class is a collection of similar objects with similar structure and behavior organized in what we call a class hierarchy. So the idea is you can the idea of this stuff, without going into too insane levels of detail, the idea of you can have a kind of a high level object like a say sport. So we say sport is kind of a high level object. All right. And then, and what we put in there, there's like objectives and rules and stuff like that. And then you can have, uh, you know, different types of sports. So you'd have baseball, football, basketball, volleyball, so on and so forth. All right. So the class hierarchy would be, there would be a, sport as kind of the parent, and then all of these different other classes, the individual sports would be the different classes would have kind of a common core, but then specific, it would have its own specific requirements that kind of come along with. So this idea of inheritance. So what you would do is the stuff you see at the child level is there's certain things we would inherit from the parent class. All right, so obviously the rules of the game, objectives of the game, things of that, that's part of the parent class. And as we create every child will have its own version of the rules and objectives and outcomes, whatever. And then UML, Universal Unified Modeling Language, which is actually kind of pretty well defined. I think it's pretty well used technique for describing databases. It does more than it can do more than databases. So it does databases, but it also does programming, and it can be used for programs and for class models for applications. So this is, it's obviously the unified modeling is okay. Yeah, you can use the same modeling techniques to describe anything. So this is kind of a pictorial representation. This is invoice object representation of an invoice, or excuse me, of a invoice customer line item. So it's customer and invoice. A UML definition of it, and then an ER model. Once again, all three of these basically represent the exact same thing. It's just a different way of representing the exact same construct. So we talk about big data, right? So Data, one of the things that's happened is that data, the amount of data we're dealing with, has grown, continues to grow, has grown in, particularly over the past 10 years, the advent of like cell phones and social networks, or smartphones and social networks and e-commerce and things of that nature. The amount of data we generate, personally generate on an ongoing basis is very significant. All right, so what's happening is as we're generating this stuff and it's being captured, you'd like to be able to process it. All right, and the challenge is as you get larger and larger. So relational databases, couple million rows, it can do that standing on its head. As we get larger, as we start getting into the billions of rows, the ability to manage that and be able to work with that is really has really become a problem. All right. So the challenge is to trying to work with this stuff, and there's really the characteristics we see with this just in general is this idea of the volume of data, the velocity of data, how frequently, how fast it's coming in, and then the variety of data, which is how many different ways do we see things, the complexity of the data. Do you have a lot of, you have a whole bunch of the same thing, a whole bunch of different things? Does it come in? Is it coming in? Hourly? Is it coming in by minute? Is it coming in by millisecond? And then the volume, just basically, is it a gigabyte? Is it a terabyte? Is it a petabyte? So on and so forth. All right. So that's this idea of big data. One definition of big data is a data that is so big it breaks it breaks your relational database. Relational databases don't work with big data that well. So as we say here, the big data challenges. Volume of it does not allow for the usage of conventional, aka relational types of structure. It can be expensive. And then, what they discovered as you're trying to work with this, a lot of the tools that were developed, a lot of these, analytical tools and whatnot that work great against relational systems, really are kind of inconsistent dealing with unstructured data. Right. So what we have is really a whole bunch of new technologies that are designed to work with big data. All right. So we've got, and a lot of this stuff was developed. Not the only, it's not the only organization, but probably one of the bigger organizations that are in this space is Google. Primarily because Google works with database, the internet-sized data sets. Part of what Google does is they read the entire internet. It's taking about 40 days, and I don't know if that's still the case to update all of their indexes. Basically, so what they do is they crawl the entire internet and find everything, and then create massive indexes around it, which lets us be able to do searches. All right. Part of that, they actually developed a whole bunch of technology. So the big one they did is something called Hadoop. All right. And basically, what it is, it's basically a tool, processing tool. It has its own. They created its own distributed file system to be able to store data, and it uses an algorithm called MapReduce. But the idea is you can take a huge data set and take maybe 1,000 servers or 20,000 servers, and basically run Hadoop on it, executing this MapReduce algorithm, and be able to process all petabytes of data and do analytical work on it. All right, so this is this is kind of a whole new generational thing. This has really kind of popped up within, say, the past 10, 11 years, 10 to 12 years has really been kind of the era of big data, and quite frankly, nothing's going back. So we just continue to get bigger and bigger and bigger. So NoSQL databases, it's not based on the relational model, kind of different techniques. The idea is it can be run in a distributed fashion, provides high scalability, high availability, fault tolerance, can process. It's designed to process large amounts of sparse data, and it's performed towards kind of processing large amounts, processing efficiently processing really large sets of data. All right, it does not necessarily replace relational databases. So people are not going out and saying, okay, I've got all my production databases. I'm going to replace all that stuff. I'm going to make it NoSQL. It really is kind of a whole new type of database processing. It kind of came out of the fact that data sets grew and grew and grew and grew. All right. So this is a kind of a key. So we'll give it kind of an example right here. This is our relational model. All right. So I've got a driver, all right, 2732, who has different types of entries in a table, which then also matches up against data in a this is a representation of the difference between. So what happens is this: a lot of these NoSQL is based on what we call the key value model. All right. So this is the traditional relational database model. This is the key model. This is what you see being used for things like big data systems. All right, so you can represent things different ways, and this is designed so that you can go through and take a large data set and have it processed in parallel by like 20,000 systems and be able to be able to process it just looking at the keys and the values and bringing things together. The trick with Hadoop is actually the algorithm is pretty simple. It's not a super complicated thing, which basically allows you to scale it almost infinitely. All right, as opposed to these relational models, which actually are good up to a certain point, but after a certain point they start breaking down in terms of their efficiency of being able to work with larger and larger sets of data. So the evolution and kind of our if you wanted to follow our kind of the history of this stuff, in the 60s and the 70s, all through the 60s, we saw like hierarchical and network databases were really kind of the predominant model. In the 70s, we started seeing the idea of relational models, and kind of evolving that. This is not quite, it's not quite as cut and dry. It wasn't like we got to 69 and things stopped. All right, what ended up happening was these represent more kind of the mainstream when as things were moving into mainstream. So hierarchical and network all ran through the 70s into the 80s, and actually probably even running it now. All right, so it's not quite we draw a line here, but it's a rough approximation. So the idea of hierarchical network databases followed by kind of a relational model, semantic model. In the 80s, we saw kind of a object-oriented, extended relational models. And then really what we saw was the internet, the rise of the internet, is really the thing that has driven this idea of big data. We can get more, larger and larger and larger and larger amounts of data that we want to be able to capture and process. All right. Just some basic terminology. And so we've got, each one of these models, whether it's a file or hierarchical or network or relational, have their own kind of terminology. So what we look right here is we're focused on a lot of what we're going to be focused on is the relational model. So the idea of a group of vendors is stored in a table. A single vendor is stored in a row, aka a tuple. A contact name, which is part of that single vendor, is a table attribute or a field. And then the vendor identifier would be what we call the key, the unique attribute, which gives us the ability to find that identifies that particular vendor amongst the thousands or millions of other vendors that are out there. No, actually not a big, particular view of kind of this idea of, what we're doing as we're doing designing databases and kind of putting this stuff together. This whole idea, it's really one of abstraction. All right. So what we've got is this idea of a conceptual model of something. So what we're going to do is we're going to take something, do business events or processes or whatever. All right. So we're going to take that as a starting point. We're going to create a designer's view, or what we call a conceptual model, all right, which kind of captures all of the different aspects, what the rules are, things like that. And then we're going to translate that into what we call the internal, which is really the database. This is the structure represented in an ERD, this internal model here, DBMS view. And then once we're done with that, once we've created that, from there we will create a physical model, which is where the thing is ultimately stored in a computer system. All right, so that is all. We don't have to know where that's at or for exactly where something is located, because quite frankly, the DBMS is the thing that will handle the translation of the internal model, kind of what we see in the ERD, to what we call the physical model, right, where the data is physically stored and where we get it. As we said, external view, end user's view of the data environment, we're kind of using entity relationship diagrams. External schema. So this would be like an example of a college. So we've got the relationships between student registration. So students enroll in a class, and there's different courses. A course can have many classes associated with it, right? Because a class is limited to 35. This is really just, this is kind of an ERD representation of it. Conceptual model, as we said, represents the global view of the entire database by the organization. So conceptual schema, basically we use it for the identification and high-level description of the main pieces, the tables. Macro view of the data environment, and really, there's no software hardware at this level. So there is no, the only thing we're really doing is we're creating a structure. All right. The logical design is basically being able to take this, creating a conceptual model. That's what the logical design is about. So once again, we have another, kind of the conceptual model, which shows you all the different. So in here, these are two separate. These are viewed as really two separate models. In this case, we assemble them together for the conceptual model for the entire database. So we have obviously students and professors and enrollment activities and classrooms, and everything is now assembled into one. So the conceptual pulls all of these different things together. As you can imagine, the bigger the organization, the bigger the operation, the more complicated this thing actually gets. And then the internal model represents the database as seen by the database, the database management system, which basically is designed to take this, these schemas and then turn them into physically, to where we physically store stuff on a disk somewhere. All right. Software, software and hardware independence. It's logical. You can change the model, change internal model without the conceptual model. So this is our kind of taking the conceptual model and creating a table. So this actually becomes closer to what we see in a real database, what a real database will look like. This create table with the field names and the description, basically the attributes or characteristics of each of these attributes. Professor's last name is a 15-character field. Professor's initial is a 1-character field. All right. And then the physical model. Physical is the lowest level. All right. Describes the way data is stored on storage media, like disks and tapes. You got to. This is a whole process. This is, the database administrator and the systems people are the ones responsible for setting this stuff up. Usually, you will not see the, business users. They don't know. All they know is they enter a command, they get the results back. But ultimately, this stuff is stored somewhere on a computer system. And where that at is really kind of defined by, the people who are managing the hardware and the databases. All right. This whole idea of the relational model, it's focused at the logical level. All right. So to use a relational database, you really would just need to understand what the logical level is and execute against that. The physical stuff will, is each database management system is designed to handle each, the representation of that in a physical form. So what will happen is you can actually take these, if we focus at the logical level, what the tables look like, you can actually take the same structure and install it in one, have it run in one database, and take the same logical structure, put it into another database, Right. Now the DBMS will actually take that each DBMS will take that logical definition and translate it into its own physical. All right. So the physical is basically you're running software on a computer which has X amount of storage or certain types of storage. That's all the physical stuff. So just a kind of a model here of our you know, data abstraction, kind of our model here: external, conceptual, internal, physical. And that is the end of our section on data modeling.